the surface integral of a function whose domain is in R3, so these are the functions that we cannot do a graph, right? Since the domain is in R3, so we will need 4 dimensions to draw these ones. So the surface integral of a function like this will be defined as the function evaluated at the surface multiplied by the magnitude of the normal vector. The normal vector is calculated by the cross product of Ru and Rv that we have seen before, the ones obtained by calculating the partial derivatives. Observe that this is a double integral over a domain in R2, as we have seen before, and the function evaluated at this parametrization is going to be a real number, and this is a magnitude, it's going to be a real number too. So here we have a numerical function, and so the domain is in R2. So this is a familiar integral that we know already how to calculate. So for instance, let's calculate the integral of this function. So this will be the function f of x, y, z equals z, right? So this is the function just z. And we are going to calculate the surface integral of this function over this surface here that is parameterized with these constraints here. Let's start writing everything we need to calculate this surface integral. First, we are going to need the function, which I said that this function is given in the problem, right? It's equal to z. But we are going to need to evaluate this function at the parametrization. That's what the formula calls for. So the parametrization in this case is this one. So instead of x, y, z, we are going to put these values. In this case, there is only z to evaluate, so the result is going to be just b. So we have already then part of what we need, that is the function evaluated at the parametrization. Now we continue looking at the parametrization because we are going to need the derivatives of that parametrization. So the derivative with respect to u, we're going to get all the variables here and do all the derivatives with respect to u, all the components here. So this is going to be the derivative of cosine of u is minus sine of u. The derivative of sine of u is cosine of u. And the derivative of v is 0 with respect to u, right? And the derivative respect to v of each of the components here is going to be derivative respect to v here is just 0, does not depend on v. Derivative respect to v here is also 0, and derivative respect to v here is 1. So we have the two vectors that we need in order to calculate the cross product that we need in order to calculate its magnitude afterwards. So the cross product is calculated by writing here I, j, k, and now we put this vector as the second row and this vector as the third row. And now we just calculate this determinant that will be I times, and so we eliminate these two and multiply this determinant, which is cosine of u minus 0. So the first one will be just cosine of u minus j times, eliminate this, is going to be minus sine times 1. So this is going to be minus sine. And plus k, we eliminate these two, is going to be 0 minus 0. So this one is going to be 0. Okay, so the vector then that we need to calculate the magnitude of is going to be the vector cosine of u. Here will be minus minus is plus. This is sine of u, 0. Okay, so we finally calculate the magnitude of this, then the magnitude of this vector is going to be the magnitude of this, the square root of cosine square plus sine square plus 0, which is the square root of 1 plus 0, which is root of 1, which is 1. So we got the two magnitudes that we need to multiply to calculate this integral, right? So we get the function, evaluate theta the parametrization, and we got the magnitude of the normal vector. Okay, so then finally the surface integral then over the surface S of z ds is going to be the integral over the domain d that is going to be given by this. This is going to be 0 to 2 pi of the integral between 0 and 1 plus cosine of v. And in here we are going to multiply the two things that we obtain, v times 1. V times 1, and so here is going to be dv du. So this will be the integral between 0 and 2 pi du. We leave this for the end, and we are going to calculate first this integral. Integral of v is v squared over 2, and this is going to be evaluate between 0 and 1 plus cosine of u. Observe here there should be cosine of u. And so we do this evaluation. I continue here, and this is the integral between 0 and 2 pi, and we are going to evaluate here v at 1 plus cosine of u over 2 minus, and now we evaluate at 0, that will be 0 squared over 2, and this is du. Okay, so we got that this is the integral between 0 and 2 pi of, we expand this square here and we take the 2 out. This is 1 plus 2 times cosine of u plus cosine square of u du. So we integrate now each of these terms of the addition. So this is 1/2, and the primitive of 1 is u. The primitive of cosine is sine, so we get here 2 sine of u plus the primitive of cosine square of u is u plus sine cosine over 2. And now we evaluate between 0 and 2 pi. So we evaluate first at 2 pi, and it will be 1/2 times. We evaluate first at 2 pi, so that will be 2 pi plus 2 times sine of 2 pi, which is 0, plus here will be 2 pi plus sine of 2 pi is 0 over 2. And when we subtract everything evaluated at 0 will be 0, so then this is the final result. So this is 1/2 times, here is plus pi, so the final answer is 3 pi over 2. So the surface integral of this function is equal 3 pi over 2. The surface integral of a vector field, so now it's not a function but a vector field, is defined as, so this is the surface integral of the vector field, and is defined as the double integral over the surface of the dot product of f with the normal vector. The surface should be oriented, and then this can be calculated as the vector field evaluate at the parametrization of the surface, and then the dot product by the normal vector that we explained how to calculate before. This integral is very important in physics and is called the flux of the vector field across the oriented surface S. And essentially is going to be a measure of the flux of material, whatever material we are trying to measure, that is passing through the surface. So if the flux is positive, we have things leaving the surface, and if negative, they are entering the surface. Let's calculate the flux of this vector field. So we have here given a vector field, right? The function whose values are vectors, and across the surface defined in this way. This is a paraboloid. A paraboloid in this direction. So this is the surface of the paraboloid. And we have the y vary between 0 and 1. So if we have here the value 1, so this is the piece of paraboloid. So the surface is just this piece of the paraboloid oriented outwards. Okay, so let's start calculating everything that we need in order to calculate the flux. First of all, let's write down this the parametrization of this surface. So this surface is given by all these circles here. So x is going to be equal to u cosine v, and z is going to be equal to u sine v. And then y is going to be equal to the square root of this plus this, which is just u squared. So these are the parametric equations of this surface, where the value of u is going to vary between 0 and 1 to get just that part of the paraboloid, and b is going to go, the angle here is going to go all the way around, so it's going to vary between 0 and 2 pi. Okay, so this is the parametrization of the surface S, and now what we need is to evaluate the vector field at that parametrization. So the vector field in this case is this one, so we are going to substitute x, y, and z by their values in the parametrization. So then in this case it's going to be 0, nothing to substitute there, y, so y is going to be u squared, and minus z is going to be u sine b. So that's the vector field evaluate at the parametrization. And now the two things that we are going to need, as before, is Ru, that is going to be the derivative of the parametrization with respect to u. So in this case it's going to be the derivative here respect to u is going to be just cosine v. Here respect to u is going to be 2u, and here respect to u is going to be just sine v, that acts as a constant, right? And Rv is going to be equal to the derivative respect to v. U is a constant that goes out, so it's the derivative multiplied by the derivative of cosine, which is minus sine. So it's minus u sine of v. And then the derivative here respect to v is 0, and then the derivative here respect to v, as before, is going to be u cosine of v. We need to calculate the cross product of these two vectors. This is the second row, and this is going to be the third row. So the determinant is going to be I times this minus this. This is going to be just 2u times u cosine of v minus j, and so the determinant, when we eliminate this, should be this times this minus this other 2. and plus k. We eliminate this is 0, will be minus this, that will be minus minus plus, so that's going to be 2 u squared. Here when we take u as a common factor, gets u multiplied by 1, and so with a minus in front, this is just minus u. So this is the vector then that we need to calculate the dot product that we need for the formula. So let's do then now the dot product. So the vector field evaluated at the parametrization we had calculated before and was 0 u squared minus u sine b. And now we need to do the dot product with this one that we just calculated. So the dot product will be this times this, which is 0, plus this times this, which is minus u cubed, and this times this, which is minus 2 u cubed sine square of b. Taken here minus u cubed as a common factor, multiplies 1 plus 2 sine square of b. So this is then the integrand that we need in our double integral. And then the flux is going to be equal to the integral from 0 to 2 pi, that was the variation of the b, of the integral from 0 to 1, this was the variation of du, and the function that we have to integrate is this one. So that will be minus u cubed 1 plus 2 sine square of b. Okay, so now we integrate this function. We're going to have integral between 0 and 2 pi of, and so integrating this function here, this is with respect to u, so all this part is a constant, right? I mean, all this part is going to be out of the integral, and we are going to integrate just this part. So this part will be a constant, I leave it out, so that will be minus 1 plus 2 sine square of b, and the integral of u cubed will be u4 over 4 evaluated between 0 and 1. I still do the evaluation before doing this final integral. So the evaluation of this between 1 and 0 is just 1 minus 0, which is just 1. And so this is going to be then minus this as it is times 1/4. Taking the minus 1/4 out of the integral, we are going to integrate just this part. And so this is going to be minus 1/4, and the integral of 1 respect to b is just b plus the integral of sine squared will be 2 times the integral of sine squared, which is b minus sine cosine over 2. And this is going to be evaluated between 0 and 2 pi. It's minus 1/4, and inside we're going to have here b plus b, which is 2b minus sine cosine, evaluated between 0 and 2 pi. So let's evaluate now at 2 pi first. So then this is going to be minus 1/4 time, evaluate at 2 pi, we're going to have 2 times 2 pi here, which is 4 pi. This part is 0, and then minus, and when we evaluate at 0, everything is 0. And so the final answer here is going to be just minus pi. So the flux over the paraboloid that we saw before is negative. It's negative and equal to minus 3 point something, so there is more material entering the surface. In case that the surface is given by the graph of a function defined this way, so in that case we can consider z minus g x y equals 0, and so when we do the derivatives, the partial derivatives here, we are going to get that the derivative respect to x is going to be minus derivative of g respect to x. Derivative respect to y is going to be minus derivative of g respect to y. And derivative respect to z is going to be just 1. And so multiplying that by the components of the vector field, I mean the dot product, we're going to get that the expression of the surface integral is actually like that when we have the surface given as a graph of a function like this. And this formula can be deduced also if the graph of the function is given in any of the other variables, like y function of x and z, or x function of x and y. So for instance, let's say if the surface is given as y as a function of x and z, so by doing the derivatives in that way, this will be the formula that results. Okay, so let's apply this formula in the actual problem that we just solved. Since the previous problem, the function that we actually define in parametrics is actually defined as a function, right? Y function of x and z. Let's apply then this formula, since y it will be a function of x and z, and solve again the same problem now with this formula. So this is the same problem then, but now instead of parameterize this surface, we're going to use it just as it is by calculating the partial derivatives as shown in this formula. So explicitly, the function dependent on x and z is going to be x squared plus z squared. And the domain D is going to be given by x squared plus z squared. That's what the y is, right? Less or equal than 1. Okay, so then let's do the multiplications given here. So the p, q, and r of the vector field, that product with these other partial derivatives that appear here. Okay, let's start by calculating the partial derivatives of h that we are going to need. So the partial derivative of h respect to x is 2x, and the partial derivative of h respect to z is 2z. And so the integrand that we have before will become now, I mean this integrand here will be p, that in our case is 0, times the derivative respect to x, the derivative of h respect to x, which is 2x, and then minus q, just q, that is y, and so plus r, which is in our case minus z, times the derivative of h respect to z, that is going to be 2z. And so this is going to be our integrand. So let's simplify. This part is 0, so the whole thing here is minus y minus 2z squared. Now let's write down what y is, right? Because we know that y is equal x squared plus z squared. So then this one is minus x squared plus z squared minus 2z squared. And so simplifying here, combining like terms, minus 1z squared minus 2z squared is minus 3z squared. Okay, so then this is the integrand that we will use to calculate the flux. And so the flux is going to be equal to the double integral over the domain of this expression. So we see that the domain is a circle, so we do a change of variables to polar, so we know that is x equal r cosine, y equal r sine, and we are going to have to multiply by r, right? So this is the change in the double integrals to polar, and so this is going to be then the integral where the angle vary between 0 and 2 pi, right? So we have a whole circle here, and this is going to be the variation of the angle, and inside we're going to put the integral between 0 and 1, the variation of r. And inside here we are going to put this substitute with the value in polars. So then this is going to be minus r squared cosine squared minus 3 r squared sine squared. And then we multiply by r. Let's simplify inside of the integral first. So this will be minus r cubed. So taking and minus r squared in here and multiply by this r, we get a minus r cubed that is common. And then multiply by cosine squared plus 3 sine squared. And so this is the r, and so this theta. Let's integrate now this with respect to r, and so then this is going to be the same, and so the integral with respect to r is going to be minus r4 over 4, right? The other part, all the other part is constant respect to r. And so these have to be evaluated between 0 and 1. So let's do the evaluation now. So that will be the integral between 0 and 2 pi. And so evaluating, the only thing to evaluate here between 1 and 0 is going to be just the r to the 4. Evaluated between 0 and 1 is just 1. And so the result here of the evaluation will give Now we take this constant out and we integrate. The integral of cosine squared is, and the integral of sine squared is the same, right? But with a minus. And this should be evaluated between 0 and 2 pi. Now let's evaluate. This is going to be minus 1/4. When we evaluate at 2 pi, we're going to have here 2 pi. This part is 0, and so just 2 pi over 2 plus 3. Here we put 2 pi. This part is 0, right? Because sine of 2 pi is 0 over 2. Minus, we evaluate at 0, but now the whole thing is 0 here and here too, so is the whole thing minus 0. Okay, so let's do these operations. This cancel, so we have here minus 1/4, and we have here pi plus 3 pi, so just 4 pi, so the final answer is then minus pi. That was, of course, the same result that we obtained calculating this flux by parameterizing this surface instead of applying the new formula that we are seeing now.